Thanks for the introduction. What I want to discuss with you today is some technological work that we've been working on that relates very strongly to sensory augmentation. And we call this thing augmented interoception, in analogy to exteroception, our ability to sense what's outside of our body, proprioception, the way that we sense our body, its orientation in space. Interoception is really about the signals that we can sense within our own body. So we're interested in what we can do with those kinds of signals in terms of sensory augmentation. So we know when we look at kind of one of the histories, and let's start at the 60s, we could go further back, obviously. We could start with Bagherita's famous experiments about seeing with the skin, where you use a mapping of a video image to map that to tactile stimulation. And with enough training, you can at some point learn to find some correlations between the images that you actually perceive through the tactile simulations. And we can move this all the way up to all kinds of experiments, for example, wearing devices that vibrate in the direction of the north, stuff that we usually are not able to do on our own. But with technology, we can learn to kind of integrate these kinds of artificial senses in our sensory spectrum, if you can call it that. So one of the ideas behind these technologies is that works through some kind of mapping. So you have something that you cannot sense on your own. You can use technology to sense it, such as the magnetic north. And you can translate that information in real time to something that you can perceive, actually, such as a vibration towards the north or a sound that you might be hearing. And in that way, you can actually start to perceive those things that you normally cannot. So we're interested, like I said in the beginning already, if you look at all these examples, most of these examples are about finding new ways to sense more of the world around us. But actually, there's a lot of senses that we have that we use to sense our own internal states. For example, we have senses that respond to our endocrine system, to hormonal changes, to blood pressure, so forth and so on. So the interesting thing is that these have quite strong connections with our emotions, well-being, our thinking, cognition. So, for example, if you imagine a situation where you're in a stressful exam and you feel that your heart is racing, then actually your heart is giving you a signal that there's something going on. Actually, it's a signal that belongs to kind of the stress signal, you could say. So it's actually your physiology communicating with you, and you're able to pick that up. So we're interested in the question, what happens if we augment the kinds of bodily signals that we might not be able to actually sense consciously? Perhaps we're not able to sense some of these kind of signals at all, even though they might have impact or signal something of interest to our own emotions and cognition. So we figured let's do some studies with that. So the first question is then, of course, what kind of interoceptive signals are there that we are usually not consciously aware about? So one of the interesting ones, I think, is the eye's pupils. Of course, it responds to the light, and that's the biggest response that it has, basically. But if you put people in a room where there's dimmed light and the light conditions are stable, you actually see that it responds to other things as well. It also responds, for example, to changes in our brain in terms of its neurochemistry. So the neuroendocrine changes, especially in noradrenaline, so something that has to do with arousal, for example, and focusing in response to, related to adrenaline in response to focus and defocusing, cognitive load, and all kinds of interesting things that say something about our own thinking processes, stuff that happens in our own minds. So we figured, what happens if we then augment that signal? Usually we cannot perceive our own pupil size. So what happens if we use an eye tracker and we turn that signal, the pupil size, into a changing sound in real time? Can we then learn something new about our own thinking processes? or at least can we learn something? So we did a first exploratory experiment, or not an experiment, it was just an exploratory study. And basically we made this little system that maps in real time your pupil size that's captured by an eye tracker uh, into the volume of a sine wave that's just continuous, more or less. So we asked 20 people to use that device. We gave them a range of thinking tasks, among other things, mental arithmetic, of which we know that it should actually cause changes in pupil size that have a relationship with the thinking process. We asked people to report the contingencies, so the correlations between the sounds that they were hearing, in other words, their pupil size, and with the kinds of changes in their thinking process. So the idea is that if these changes coincide, that maybe you pick up on that. So if the sound changes, the moment something in your thinking changes, you might learn something actually, but oh wait, so this is related. So we asked those 20 people, and if we don't give those people instructions and we'll let them do the thinking task, then about 55% notices a relationship that you could loosely relate to cognition, to thinking. So for example, for people, when they used the device and they were thinking deeply, they noticed the change in the sound. And when they started to concentrate on something, they noticed the change in the sound. So 3 more. Now, when we, after a little bit later, when we told them actually what the signal was and that it actually had the correlation possibly with the thinking processes, then this number went up to 75%. Now, obviously, this is also a work in progress, right? So this is a first little look that we did. And this seemed somewhat positive, but there were also some weird things. For example, some people experienced positive feedback loops where stress seemed to cause changes in the sound that they were hearing, so changes in their pupil size, but the fact that they heard that sound become louder also caused even more stress. So, at some point, obviously that stopped, but it was one of these byproducts that we didn't expect, but it wasn't something that we want, obviously. It was quite a negative experience for a few people. So that was an interesting one that by chance we picked up with a few participants. So then we moved on. We did a slightly bigger study. We did the first small experiment with 75 people. And we thought, well, we need to be a little bit more rigorous. So we used the real audible pupil size, the real mapping from the eye's pupil size to sound. And we used what we call sham audible pupil size. The sounds and the fluctuations sounded the same in terms of the timbre, in terms of the oral characteristics, but there was no correlation in the sham condition with their actual pupil size. It was just random fluctuations in that sense. And again, we let them do several thinking tasks, but this time we also asked them after each thinking task to self-report the degree to which they felt they learned something about their thinking processes. Again, referring to their ability to pick up these correlations between changes in pupil-sized sounds and their thinking. And we got some mixed results. So one thing, usually if you want to compare these two different groups, so the sham audible pupil size and the real audible pupil size, you want to check whether there's a difference between the means that's worth having another look, having further research. In other words, whether this difference is significant. But as you can see, you basically see 2 peaks in the data. So it doesn't make any sense to actually calculate the means and try to compare those. This data is bimodal, we call it. So you do a different kind of analysis, and basically you look for each measurement point in the item. So basically, if there's low agreement with items that are used to answer questions about how much they learned about their thinking process, or whether there is slight agreement or strong agreement, you can check where perhaps there are differences. What's quite interesting is that what we found actually was that the real audible pupil size tended to decrease the likelihood that people did not learn anything about their thinking. And it also tended to decrease the likelihood that they reported slight disagreement. But what was also interesting is that there were no differences between the real and the sham audible pupil size for actually stronger agreement. So in other words, people that reported that they really learned something about their thinking, they reported that more or less equally in the sham audible pupil size condition versus the real audible pupil size condition. So one of the conclusions is actually that real audible pupil size led to a bit less uncertainty about whether knowledge about their own thinking processes was learned, but it didn't lead to much more certainty, actually, than when they used the sham audible pupil size. So there's quite a few questions about how to progress this research and to develop this concept of augmenting our interoceptive senses. So I have a few conceptual questions, but of course, if you have other things you want to talk about later in the session, that's also fine. There's some clear design challenges, such as trying to prevent that positive feedback loop between stress and the sound. But also a bigger question, perhaps, is the question, should we really augment the kinds of interoceptions that we usually don't, so the kinds of signals that we usually don't have access to? Because apparently evolution decided not to give us very strong access to our own pupil size. So maybe there's a good reason for it. I don't know. So there's a bunch of questions we can talk about. So thanks. Thank you for listening.